Welcome to this lecture series in real analysis. We're starting a new module which will be about infinite sums, and it is a most interesting concept in mathematics. Algebra or arithmetic is about adding finite things, right? We can add 3 and 5, or we can add 3, 5 and 7. But with the tools of analysis, we can now form infinite sums. We can possibly add infinitely many numbers. Not always, the sum is not always meaningful, but many a times it is. And this is something that is unique to analysis. This is in some sense a prized possession of analysis, if you will. Anyway, so we'll see all the details. Let's not recall anything. I don't want to recall anything. It's just a fresh module. Okay. So here are some problems for practice. And now let us get started. So let me start with an age-old paradox. This is due to Zeno from ancient Greece, I suppose. And what he stated was, well, I'm not going to paraphrase, but here is essentially how I understand the paradox. So imagine we have a line segment of length 1. So 0 is the starting point and 1 is the ending point. And suppose there is some snail here, which I'm representing as a blue dot. So there is some snail who starts at the left end point and who travels at 1 meter per second. So this whole thing is 1 meter apart, meaning from 0 to 1, it is 1 meters. And the snail travels at the speed of 1 meter per second. It's a very fast snail, come to think of it. Anyway. So what Zeno argued was, well, there must come a time that the snail reaches exactly half of its final destination, right? He manages to cover exactly half the distance that he was due to cover. Okay. And then there must come a time when he has covered exactly half of the remaining. And then there must come a time when he has covered exactly half of the yet other remaining segment, and so on and so on. So it seems like there are infinitely many steps involved in this process, and therefore the snail should never reach the end. Right? It sounds like no process should ever finish. It is taking infinitely many steps to complete even the simple process of walking with a constant speed. So this is a paradox. It's not a contradiction. It's a paradox. It is puzzling as to what's going on. And the theory of infinite series addresses this question. Of course, there is no way to fully resolve this in a certain sense. But whatever we are going to do is going to at least address this paradox. Whether or not you will be convinced is another matter. All right. So let's get started with some formal definitions. So suppose we have a sequence of real numbers, then this symbol, this horrible symbol, which looks like we are adding infinitely many things, but as of now it is just a formal object. Let us not try to think of it as this being an operator on an or anything. It is just one symbol. Let's just think of it as one symbol. And this will be called the infinite series associated with the sequence. Infinite series associated to the sequence that we started with. Unclear what are we even exactly saying. All I am saying so far is that to this we have associated a symbol, nothing more than just a symbol. Right? But anyway, let's play along. So this symbol may also be equivalently written as follows. Right? Just an alternate notation. Of course, it looks like we are adding a bunch of things, but as of now, no. So far, no. It's just a formal thing. Okay. And now, the nth partial sum of a given infinite series So every time we form an infinite series, we are not going to say that let an be a sequence and this be the corresponding infinite series. We just start with the symbol and call it an infinite series. And the nth partial sum of this infinite series is defined as the sum of the first n things. So in symbols, it is starting from 1 going up till n. Lack of space, sorry. This is a meaningful number. This is addition of n things. Sorry, this is an AK, I apologize. This is AK. Right? So this is a sum of n things. And therefore, it is a meaningful real number. All right. And let us just take one example. We can take this as the following sequence. The nth entry in this sequence is the nth natural number. And you can form the corresponding infinite series. So admittedly, this is a very empty discussion so far. What are we doing? I have just introduced a meaningless symbol to any sequence and also defined an associated sequence of sums. Given a sequence, you can associate to it another sequence, namely the sequence of nth partial sums that we associate to the corresponding infinite series. Of course, you don't need to write the infinite series to form nth partial sums. Given any sequence, you could have just said that let me just add the first n terms of the sequence and call it the nth partial sum. So yeah, I agree. As of now, this may not feel like much because it isn't. So let's move on. And now the thing will have some real content. So suppose we have an infinite series. Then we say, let's say the infinite series is this guy. Then we say that this thing converges if the corresponding sequence of nth partial sums converges. Right? We already have a notion of convergence of sequences. So the sequence of nth partial sums, is a sequence. So we can ask whether or not it converges. And we say that the original thing converges if the corresponding sequence of nth partial sum converges. And what are we trying to say? Well, this infinite sum, whatever this was, let me write it. Let me use the symbol k to denote the kth entry rather than n to denote the nth entry. So we said that we can alternately write it like this, just a notational change. So suppose this converges, our infinite series converges, then what are we saying? We are saying the more terms you take, the truer the value becomes. Since the sequence of nth partial sums converge, it's like the larger the number of terms you pick starting from the beginning, the more representation or the more of the original infinite series you have picked up, and therefore the more you are able to simulate whatever this sum was trying to capture. So it's a meaningful object that you associate to any series, right? Of course, if the thing doesn't converge, you can't ask for the limit of the nth partial sums. But if the thing converges, if there is a limit to the sequence of nth partial sums, or let me just say to the sequence of partial sums, then that does sound like the number that this was trying to be, that this formal object was trying to be all the while. Okay. So, yeah, and in this case, we call this I should have written it here somewhere, but let me write it here. So if this converges, let me use a k. If this converges, then the limit of the nth partial sums, and the nth partial sum is this thing, is called the sum of the series. Just some name. Of course, this is an obvious name. whatever this limit is, if it exists, is called the sum of this series, or just equal, or we in fact even write this symbol equal to that. In that case, we just what we write is, we just write that this thing is equal to this, whatever this limit is, right? So in case the series converges, we may think of this now as a number. So initially we were just saying this is a formal symbol that we associate to any sequence. But when this thing converges, now we can pretend, or we can think of this as a number. So this kind of abuse of stance is fine. Once it converges, we'll regard this as a number. And what number? This number. That's the definition. Okay. So anyway, let me take examples to illustrate the point. So here, suppose my sequence was an being the nth natural number, then the corresponding series, is it convergent? Well, the sequence of nth partial sums is certainly not convergent. It is strictly increasing, and increasing without bounds. So this is divergent. I mean, if the thing doesn't converge, you call it divergent. So this is divergent or not convergent. It is a divergent sum. That's also something that we say. Similarly, this guy looks a little bit more well behaved. The nth number is plus or minus 1 according to the parity of the natural number n. So if you take the nth partial sums, it fluctuates. If n is odd, it is minus 1. If n is even, it is equal to 0. Right? So it is either 0 or minus 1. 0, minus 1, it fluctuates. So the sequence of nth partial sums again doesn't converge. The nth partial sum is not faithful, is not converging to any value, it is fluctuating. So again, this is divergent. I defined convergence, but I'm giving examples of divergent series because it is not so easy to give examples of, or not so easy to prove any times when such a thing converges, or when you have a convergent series in hand. But we'll see examples of convergent series in this lecture. Let's just wait for a while. Okay. So now, a necessary condition for convergence. So what are we saying? Suppose we have a convergent series given to us. Then we are claiming that this must necessarily happen, that the nth term must go to 0. We are not saying if this happens, then the reverse happens. We'll see example where that's the case, where where the nth term converges to 0, but still the series doesn't converge to anything. But one-way implication is true, meaning if the series is convergent, then the nth term of the sequence which formed the series converges to 0. We are not saying that the sequence of nth partial sum, we are not making a comment about the sequence of nth partial sums that is there in the hypothesis. The hypothesis has it in it that the nth partial sums converge. That's exactly what the statement is. We are making a comment about the sequence that formed the series. Okay, enough talk. Let's prove this. Of course, you should pause the video and prove such things yourself. So it's very simple. Suppose let me write Sn, or maybe little Sn as the nth partial sum. We are given that this converges. This is a convergent sequence. That's exactly what is given. All right. Say the limit is S, but therefore so is the limit of this guy, clearly, and thus the difference converges to S minus S. And that tells us that the n plus 1th term goes to 0 as n approaches infinity, which is same as saying that the nth term goes to 0 as n approaches infinity. Very simple. I mean, the formal details are fine, but think about it. If this was not happening, the sequence of nth partial sums will accumulate something, or I mean, you can see it intuitively, but let me leave that to you. This reasoning is very simple. You can also gain some intuition by means of this reasoning, but this is a fairly intuitive claim. All right. Clearly, if all the terms were positive or non-negative, then you can immediately see the importance or the necessity of this statement, right? So anyway, and now hopefully we can see examples of, or soon we can see examples of convergent infinite sums or infinite series. Yeah, so this is an example of a convergent infinite series. In fact, it's more like a theorem. You pick two real numbers and suppose a is non-zero. I mean, this was not, okay, let's say a is non-zero. Then this infinite series is convergent if and only if the magnitude of r is strictly less than 1. So in high school, you must have read geometric progressions. This is an infinite geometric progression, and good chances that you must have also read the formula for the infinite sum of an infinite geometric series and so on. So that's exactly what we are trying to make precise now. So this is an infinite series. Here we're starting with the symbol 0 rather than 1. We're starting with 0, and I don't want to beat down such simple, silly, trivial things. You can start with not necessarily the index 1. You can start with other indices. 0 here. You can also start with 3 if you like. Okay, but here we start with 0. So the first term of this whole sum is a. The second term is ar. The third term is ar square, and so on. Right? Okay, so yeah, so we want to show that this converges if and only if this is the case. But I will not do this in so much detail. First, we'll just observe, or maybe let me do it. So what is the nth partial sum? The nth partial sum, or let me define Sn as starting from 0 to n, ar to the power k. This is the nth partial sum. It's a sum of n plus 1 terms, not n terms, but that's okay. So that's Sn, and what do we want to do? We want to show that Sn converges if and only if this is the case. That's what we want to do. All right, fine. So usual trick. What is r times Sn? R times Sn is this, which we will write as ar plus k equals 1 to n, ar to the power, or yeah, maybe it would be better, let me correct it. So it would probably be better to write it this way. So k equals 1 to n plus 1, ar to the power k. So nothing changed. We have just changed the, or kind of boosted the dummy index, but we have to nerf it to compensate for it. Think about it, these two things are the same. Okay, and which is equal to, which we can write as k from 1 to n. Write it like this, and now we take the difference. We subtract these two things. So we get Sn minus Rsn as this thing. Here a lot of things cancel out, only the 0th term remains. So if you look at this difference, for k equals 1 to n, these two terms match, so they annihilate each other. So only for k is equal to 0, this thing survives. And what is that? That is equal to ar. No, this is just a minus ar to the n plus 1. So this shows that 1 minus r times Sn is a into 1 minus r to the n plus 1. And if r is non-zero, if r is not equal to 1, we can write All right, so we can do this. If r were equal to 1, then clearly this thing diverges, because what is it? It is the constant, a plus a plus a plus and so on. And since a is non-zero, this thing cannot possibly, the sequence of nth partial sums cannot possibly converge. So if r were equal to 1, the divergence is clear. Okay, so we have this. And yeah, so suppose mod r is greater than 1, then this limit clearly cannot be finite, because this is exploding. If mod r is exceeding 1, then r to the n plus 1 will become arbitrarily large. So then it cannot converge. So clearly, if mod r is greater than 1, then Sn doesn't converge. What if mod r is equal to 1? So if r were equal to 1, we have already argued that this thing cannot converge because a is non-zero. If r is equal to minus 1, then here is their flipping problem. This thing flips. As the parity of n changes from even to odd, this is flipping. So even that thing doesn't converge. And if mod r is less than 1, so in this situation, if mod r is less than 1, this dies down as n goes to infinity, and therefore you get a convergent thing. So I'm not writing all of that. Let me just leave it here, and we have established this thing. And in fact, if mod r is less than 1, then the limit of the sequence of partial sums of this series is a upon 1 minus r, precisely for the reason we just mentioned, that this thing dies down. This goes to 0 as n goes to infinity. Okay? So we in fact know what this sum is in this case. All right. And now this is an interesting example. Here, the nth terms, they are converging to 0 as n goes to infinity. But still we are claiming that this thing diverges. So even though the terms are smaller and smaller, they still accumulate to become larger and larger. That's very interesting. And it's not exactly easy why that is the case. It's not so clear. And I encourage you to think about it. It's a very important statement. It's a important statement for many reasons, but one such reason is that it's something fundamentally new to someone who is fresh out of high school, right? Why should such a thing become bigger and bigger without bounds? Unclear. Okay, so here is the proof. Here is the very standard proof. So we will write the series like this. Okay, so that's what it is. And let us club these two things, and then these 4 things, and then the next 8 things, and so on. So if we club them, and here are the next 8 things. All right, so clearly the first term is greater than or equal to half. So I'm just trying to be somewhat I want to explain the idea, so I'm being somewhat informal. We want to show that the sequence of partial sums diverges. In fact, we'll show that it grows without bounds. So suppose we have stopped at some very large n. So the first number is of course at least that much. What about this guy? That thing is at least 1/4 plus 1/4, clearly. Right? This is at least 1/4, that is at least 1/4. Okay, wonderful. Now, these 4 terms, each of them is at least 1/8. So we can add 1/8 4 times. And then the same circus. Here we'll have 16 terms. Each of them will be at least 1/16. So this is at least half. This is also at least half. In fact, now it is equal to half. This is equal to half. This is equal to half. So this is half plus half plus half. All right, so if you want to be very formal, what you would say is that if you take a suitable nth partial sum for a suitable n, it will be an accumulation of halves right? And the number of halves will be increasing as you're, where you truncate. So therefore, the nth partial sums grow without bound, and therefore this diverges. Very interesting. All right. And here is a corollary that if you take this series, the nth term being 1 upon square root of n, this diverges. This is very simple, simply because this thing dominates that guy, right? And if they sum up to accumulate more and more things, so will they. So that's that. So what we saw, that if you have a convergent series, then the nth terms converge to 0 is true, but the converse is false. Here the nth terms converge to 0, but the corresponding series is still not convergent. All right, let's move on. And here is a very interesting example. This thing converges. This is historically, was first, I think, proved by Euler using some geometry, what do you call them? Generating functions ideas. They were not very rigorous by today's standards, but they were very creative and they helped us understand things, and they called for maybe more rigorous investigations. Such things push the field forward. Anyway, so you can maybe Google this and read more about. Here we are going to give one argument why this thing converges. Unclear, not very clear why such a thing would be convergent, but it is. So we'll give two proofs. One is a very visual proof, the other is somewhat analytical. All right, so first we note that to show that this thing converges, it is sufficient to just argue that starting from 2, the thing converges. So suffices to show that this thing converges. Somehow it is easier to argue for this. And how are we going to do it? Here I've drawn this function 1 upon x square. So this function is the graph of 1 upon x square. And the value at 1 will be 1. The value at 2 will be 1 upon 2 square, 1 upon 3 square, and so on. And 1 upon 2 square is what? 1 upon 2 square is precisely this area. So let me draw it and then explain again. So this little area is 1 upon 2 square. Why is that? This value is 1 upon 2 square simply because of this function being 1 upon x square function. And this is 1 units. So the area is 1 upon 2 square, right? Similarly, the next chunk, this is 1 upon 3 square. And then this is 1 upon 4 square. And so on. Right? But this is not what I wanted to do. I want to do it the other way for a particular reason. Oops, what did I do? So just pardon this hiatus. I wanted to do something else. What I said was not wrong, but was not useful. So I will think of 1 upon 2 square as this one. This is 1 upon 2 square. This is 1 upon 3 square. This is 1 upon 4 square. And so on. Right? This length is 1 upon 2 square. We are just multiplying that by 1 to get this area. All right. So clearly from the figure, the area under this curve starting at 1 dominates the shaded area. And the shaded area is precisely that. So this is at most being a little bit informal because the symbol infinity is present here, but that's okay. You can make this precise very easily. So this is at most integral from 1 to infinity. But if you're really uncomfortable, I will write an capital N here. Integral. Now it's precise. Now it's completely formal. Of that thing. Right? Let me just be a little careful. So suppose I was doing from 2 to 2, I would say this is 1 to 2, and that is correct. Yeah, so this is fine. So we have this just by this visual thing. Of course, you can justify it properly. So we have this, but what is that guy? We know how to calculate that integral. That integral is minus 1 upon, so this is x to the integral of x to the minus 2, and that is equal to x to the minus 1 upon 1, but you will subtract out, so this becomes minus 1 upon n plus 1. So 1 minus 1 upon n. That's what it is. So as n increases, this thing will be at most 1, right? And that's it. So we have shown that this doesn't grow without bounds. It is smaller than that. So that's it. That's an argument to show that this converges. What it converges to is another matter entirely. We haven't found the limit of the sequence of nth partial sums. We have only said that that thing, whatever that damn thing is, it converges. Find the limit is another matter, and Euler did find the limit. It was pi square by 6. But those methods were not completely rigorous. Now we do have rigorous proofs for that, but probably we are not going to get into them. Okay, but there is another much simpler way. Here, this way is very memorable, it's very intuitive, it explains things, but here is an analytical way. You just observe that this guy is strictly less than that guy. You can also write a equal to sign if you like, less than equal to if you like. This is strictly less than that, which is equal to this. A little trick, if you will. So if you sum up the, sum n from little, n from 1 to capital N, here you are seeing a telescopic sum, so things will cancel out and that's it. I mean, that's basically how you can bound the nth partial sum uniformly. So that's it. That gives a nice example of a convergent series. We learned some new concepts. As of now, it may not be completely clear as to why this is so useful, but we should keep an open mind. And with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.